Hey guys, it's Mr. Stetzler. This morning we're going to go over a lesson on partitioning a line segment. So these guided notes that I have here that I'm referring to, they're available to you on Canvas if you can print them, download them, use Cami, or just simply use a sheet of notebook paper. I'm just using these as examples. I will post a completed copy of these guided notes as well on Canvas, but I'm going to go over a few of these examples here in the video lesson and also give you a formula that we'll use. It's not required to use graph paper, but you'll notice that the practice problems that I have assigned or will assign, they do incorporate a graph because there's really two methods I could use to partition a line segment. Well, what does partitioning mean? Partitioning means we're going to split a line segment into parts. Earlier in this lesson, we kind of looked at the midpoint and what a midpoint does. Well, a midpoint does partition a line, but a midpoint is kind of separate from this. A midpoint, what you've had a quiz onto, it kind of splits it. It partitions. That's a fancy word or for splitting into parts. It partitions into two congruent parts. So when we're talking about partitioning a line, typically the formula that I'm going to go over, you would not use if it's a midpoint question, but a midpoint does the exact same thing, just it's a special case. It splits it into two equal parts. So what that means often is if it's a midpoint, that means the points, it creates the distance between the midpoint and the other points is half the distance, or it's half. It's halfway from the other one. So a lot of what we're doing in this section is we're having to determine the coordinates of the point that is a given fractional distance. So this fractional distance that I'm referring to here, if it's a midpoint, that fractional distance will be exactly 1/2. Okay. So we're going to be looking at some fractional distances that aren't 1/2. This first example that I'm not going to go over with you here on the video happens to be a midpoint. All right. P is half the distance from A to B. Well, that means this is a midpoint. You could use the midpoint formula to determine the location of this new point. You can use the graph to determine the location of midpoint. I'm going to give you a more complicated formula that is for all types of partitioning, not just the midpoint. If you know it's a midpoint, use the midpoint formula or just simply go half of the distance. Okay. The second part of what we're going to be looking at is, well, determine the coordinates of the point that partitions a given line segment into a given ratio. All right. So there's two aspects to this. When I cut this point in half, and let's use this point as an example, or number one as an example. If I have point A here is at 4,2, and I have B that is at 6,0. Here's A, there's B. I think you guys could all tell that the midpoint is right there. Okay. So the midpoint, without even using the formula, you probably know the midpoint's at 5,1. Okay. Well, this point is exactly halfway. But here's what it means about those two halves. These halves are in an equal ratio. So they're in a 1-to-1 ratio. That means they're both the same. They're both the same length. So when we're talking about the ratio aspect here for a midpoint partitions a line segment into a 1-to-1 ratio. We often use a colon to separate that, or you might, we're not going to write the ratio as a fraction. If you look down here at the bottom of the sheet towards number 4, here's an example. We're splitting this line into a 1-to-2 ratio. So if you happen to see a 1-to-1 ratio, then we know it's the midpoint. So what does that mean? That means these parts are equal to each other. If we have a different ratio, like a 1-to-2 ratio, like when we get down to number 4, that means this part is twice as long as the other part. Okay. So, well, what do I do if it's not a midpoint? For example, number 2. And it says point P is 2/3 of the distance from A to B. So I'm going to plot these points. And again, I'm also going to show you a method where I don't have to plot the points. So for the first part of the example, I'm going to do the graphing method. And then I'm going to give you a formula that I could use to solve the same question, okay? So I'm going to plot the points. A is at -6, -4. B is at 6, 5. If you don't have graph paper at home, you need to get some, all right? It's kind of one of the required tools that you might need for this class. I'm going to grab a straight edge so I draw a nice straight line. Again, you can do a lot of wonderful things with the Cami app. You can, everybody should have access to the Cami app if you on your Chromebooks. If not, download it. Okay? It would definitely help you with these PDF copies of assignments. We're going to do more and more of those. We're not necessarily going to be working out of our textbook always. Okay. There's not a very good lesson on this in our textbook, so that's why you've seen the last few assignments outside of the text. Okay. All right, so I have this segment A to B, and we're trying to find the location of P, and P is 2/3 of the distance. So it's 2/3 of the distance from here to there. All right. So there's two ways to do this. And what I'm demonstrating here actually is where the formula is derived. The formula that we derived comes from the slope formula and a little bit of the distance formula. So I'm going to draw on a right triangle here, kind of an imaginary right triangle from A to B. You could have gone up and over too if you wanted to. All right. So I'm going to find kind of the length of this. And we could use length to find, we could use Pythagorean theorem to find the distance from A to B, but we're trying to find the point P that's 2/3 of the way. You know, we probably could estimate, hey, it's probably somewhere right here, but we want to be precise. We want to be exactly 2/3 of the distance, okay? So if I look at this horizontal distance, I need to figure out the horizontal distance between A and B. Well, this is at -6. That's at +6, so I know this horizontal distance is 12. And let's look at this vertical distance. This vertical distance is 9. So if you're going to use the graphing method, draw on a right triangle. Here's where the 2/3 comes into play. This point is going to be 2/3 of the way up this line. So that means it's going to be 2/3 of this 12 in the x direction. And it's going to be 2/3 of this 9 in the y direction. So if I go 2/3 of 12 and then 2/3 of 9, I should be able to find my point. So using the graphing method, and some of you are going to prefer this method, this is how you could find the location of this point. If I do 2/3 of 12, that's going to tell me how far to the right I need to run along this line. Well, 2/3 of 12, that's 24. 24 divided by 3, that's 8. So that means I'm going to go along this triangle 8 boxes to the right. I'm going to go to the right 8 boxes. Another thing that these two numbers represent, this is the run of the line, and this is the rise of the line, otherwise known as slope, in non-reduced form. And you're going to find we don't want to reduce these numbers. To find the location of this point, I have to use the entire length of the line, the entire distance between A and B. All right, so again, we just kind of repeat the process. So I know I need to go this far, but you could probably recognize, hey, I'm going to go straight up to the line. You might not even need to do 2/3 of 9, just but to show you that it's true. Well, 2/3 of 9 is 6. If I go up 6 boxes, I find myself right there on the line. And from the graph, I can identify the coordinates. The coordinates appear to be 2, 2. So we've just partitioned this line into parts, or we determine the location of a point that's 2/3 of the way up this line. So basically, we're breaking up this line into thirds. If you broke it up into thirds, this point right here would be 1/3 of the distance. So this would be a third, that would be a third, and this would be the final third. You could just go divide it into thirds and find the one that is 2/3 of the way of the line. It's another way to do it. Essentially, that's what we're doing when we're using this graphing method. We're dividing this line up into thirds, and we want to go 2/3 of the way. The whole point, and let's determine where that point's at, point P. If you want to label that, we can put point P there. Okay. Now let me give you the formula, because you know what I could do? I could take away this graph here, and we could find the location of this without, we could find 2, 2 without the graph. Okay. So I need you to write down this partitioning formula. Unfortunately, when we have an end of course exam at the end of the year, they don't let us bring in our own formula sheet. And this is one of these formulas that you got to memorize. So you got to know midpoint formula. You got to know this partitioning formula. So I'm just going to generically use the letter P. So when I'm partitioning a line, we're going to be locating the coordinates of a point that splits it into these parts. All right. Let me go back to the graph here. So this point, it splits this line into, this would be 2/3 of the line, this would be 1/3 of the line. Okay. Its location is 2/3 of the distance from A to B. I could use this graphing method, it works every time, but guess what? Some of you are never going to use the graphing method. You're going to want to use this formula, as long as you can memorize it. Okay, so to find the location of this point, we start with, well, where did we begin at? X1. All right, so X1 in the problem we were doing here would be point A. All right, so I got to start at X1, and I got to add the fractional distance. I'm going to abbreviate that with the word frac. The fraction of distance in the X direction, which we call the run. Going back to that triangle. So basically, we're trying to find, we started at point A, and we went 2/3 of this 12. The run was 12. Okay. Comma, y1. Well, this point here would be y1. And I need to add the fractional distance times the rise. Now, you might also see this formula substituted in with, well, how do I find the run of a line from the slope formula? You guys might want to write that down. It's x2 minus x1. The rise of a line is y2 minus y1. All right? So you might want to incorporate those into the formula. All right, well, what is x2 and y2? Well, that would be the other point. So if I'm using this as an example here, that would be x2 and that would be y2. Same thing you use for the distance formula. Okay. I like to just remember it in these words, but if you want to go ahead and substitute in x2 minus x1 and y2 minus y1. Now, you must do those in this order. Okay, make sure you do it in that order. Okay, do not simplify slope. I know rise and run kind of represents slope, but you always want to pay also attention to the word from. They told us to start from A. So the one that's after the word from, that's going to be your ones. After the word to, that's going to be your twos. So just to show you that this formula works for number 2, to find that point, I would just start with, well, x1 was -6 plus, well, they told me the fractional distance was 2/3. The run, well, suppose I didn't use the graphing method, I don't know the run. All right, but I could plug in these points. X2 was 6 minus x1 was -6. Be careful with negatives. You guys struggle with that in distance formula. And the y1 value is -4. Now there's a comma here. because we're trying to find a point. So it's -4 plus the fraction they told me to do, it's 2/3 of the distance, times the rise. Well, either do the rise out to the side or let's plug in the points. The rise would be y2, which is 5 minus a -4. And again, it doesn't really matter. Actually, the order does matter here, because if we did -6 minus 6, this would be a -12. So make sure you pay attention to the order. The order of these numbers is very important. In the distance formula, it didn't matter, but we're specifically starting at A and going towards B. We're not starting at B and going to A. All right, so pay close attention to that order. Okay, order is very important. All right, so I just got to do a little simplifying here. This is going to be -6 plus 2/3. 2/3 of 12. Be careful with your subtraction signs again. In negative signs, this is -4 plus 2/3 of 9. Again, two negatives make a plus. And you'll notice, hey, this is the same thing, 2/3 of 12 and 9 we got from the triangle. All right, so I know this is -6 plus, let's see, 2/3 of 12, that's 8. -4 plus 2/3 of 9, that's 6. -6 plus 8 is 2. -4 plus 6 is 2. Partitioning a line segment, we're splitting it up into parts. We're going to be using this formula to determine the location. So we're often just trying to find, well, what's the location that splits this line into a given distance, or determine the location of point that is given the line into a given ratio. That's what I need to explain next. All right, so we're going to do one more example from this page. I will post all the solutions to every example on Canvas, just so you have some more examples to refer to. We might do some others in class too. All right, so keep in mind about this partitioning formula. We're going to come back to it. So I'm going to model both when we look at number 4 here. All right, so let's look at number 4 real quick. Sorry, I got that crease in my paper, but I'll come back to that formula. So in number 4, it says point P partitions AB from A to B, pay attention to that, into a 1:2 ratio. So here we're told the ratio. Well, let me go back up here. This is actually in a 2:1 ratio. So if this one was in ratio form, this one would be a 2:1 ratio. Here's what that means. This piece from A to P is 2 times longer than this piece from A to B. So if they would have given you this problem in ratio form, it would have been 2:1. But instead they gave us the fractional distance. But the key is this fractional distance. We got to know, how far is this point from A to B? So it's kind of all about finding this fractional distance. And I'm going to give you a formula to find the frac. I call it the frac. Just keep in mind it's that fractional distance. Okay? How far up the line do I need to go from A to B? Now here's what that means. I know for sure that it's going to split it into parts, but the first part's going to be 2 times longer, or sorry, in this example, it's 2 times longer than that one. Here's what I know in this one. The first part's going to be smaller, so the first part is going to be half of the second part. Okay? So it's going to split it into a 1:2 ratio. So from A to P will be half the size of P to B, and we'll see that when we graph it. So I'm going to demonstrate, well, how could I do this on the graph? And then we'll use the formula as well. All right, so let's do this one real quick. Let's plot the points. 0, 0, -6. That's right here. And B is at -6, -3. All right, sorry, that's A. So A is there and B is there. All right, I'm going to grab a straight edge and connect those dots. Okay. Let's zoom in on this guy just a hair. All right, so we're trying to find the location of point P that splits this line into this given ratio. That means we don't have equal parts. The only time you'll have equal parts is if you see a 1-to-1 ratio. Probably not going to do midpoints again in this section. But you guys could probably narrow this down. All right, so a 1-to-2 ratio, that means the first part's going to be half the size of the second part. What I like to do is go back to this fractional distance. And there's actually a formula to find the frac. Write down this formula. The frac is equal to A over A plus B. Well, what do A and B stand for? A and B stand for the corresponding parts in your ratio. So when we have a ratio here, the first number is A, the second number is B. So to find this fractional distance in this problem, we're going to plug in 1 over 1 plus 2. All right, so my fractional distance in this problem is going to be 1/3. All right, so it's similar to number 2, where number 2 was 2/3 of the way of the line. This one's going to be 1/3 of the way down this line. All right, so basically we're going to take this line and split it into 3 equal pieces. Again, I'm going to demonstrate the graphing method. If I draw in a triangle, I know this side of my triangle is 3. It goes down 3, and it goes over 3. Over how many? 1, 2, 3, 4, 5, 6. It goes over 6. So basically, we're just going to take this fall and this run and divide it by 3, or 1/3 of it. So 1/3 of 3 is 1 unit. 1/3 of 6 is 2 units. So to find this point that partitions this thing into thirds and is 1/3 of the way from point A to B, I'm going to go down 1 box and over 2 boxes, and you should see that lands right on the coordinates -4 and -4. That's the location of our point. Now here's where the ratio shows up. This is equal to 1 part of this line. This is equal to 2 parts. Okay. If I split this up into thirds, here's where my next point would be. This would be 1/3, 2/3, 3/3 of the line. So this part is worth 2. This part is worth only 1. So this is half the length of that line right there. Again, we're not trying to find the length from A to P. We're just finding the location of the point. Okay? So I want to go back to the partitioning formula just to show you that it works as well for this problem. And I'm probably going to use this space up here. Okay? So find that point P. I would have done, well, x1, that's my -6 here, plus, well, the frac. Okay, so if you're not going to use the graphing method, and there's going to be some problems you don't use the graphing method on, where I take the graph away, but you can always use the graph. So if I took this graph away, I need to go back to the formula. Okay, let's go back to the formula. I took the graph away. So this is going to be my x1 and my y1. That's going to be my x2 and my y2. Okay. So I know this is going to be, let me get a blank sheet of paper so I have some more space to work with here. So I don't cram it in there. So for this problem, if I get a blank sheet of paper, point P will be equal to, well, x1 is this -6 plus, okay, so the formula, you always use the fraction, not the ratio. Do not change this ratio to a fraction. Some students put 1/2 always, but we have to do this legwork ahead here. We got to use this formula to find the fractional distance. So the fraction we're going to use in this problem is 1/3. So we always have to change it to that fractional distance. So in your partitioning formula here where you see the word frac, they're talking about the fractional distance. So in this case, my fractional distance was 1/3. Well, my run is very important that I go in this order. x2 minus x1. It's very important that you do 0 minus a -6. Make sure you put it in the correct order. x2 minus x1. Remember, you could always substitute those into the formula, okay, in case you don't remember how to find run from the slope formula. So then I go back to, well, the point that I'm starting from. Keep in mind, that's very important. You recognize what point we're starting from. I'm going to start at -3 and add 1/3 of the rise. Well, the rise is y2. y2 is -6. y1 is -3. Not sure why I put a comma there. So it's -6 minus a -3. Again, the most common mistake I see with the formulas is students not subtracting right. It's kind of the same mistakes I saw with distance formula. So -6 plus 1/3. I'm just doing what's in parentheses first. I know you probably do that in your head. It's 0 plus 6, which is 6. -3 plus, I'm just following my order of operations. Please excuse my dear Aunt Sally. If you can skip some steps, skip some steps. It's fine. Now, be careful. This is -6 plus 3, so that's -3. That negative is very important. If you use +3, you'll get the wrong point. You'll get a point not on your line probably, or going in the opposite direction. All right, so this becomes -6 plus, well, 1/3 of 6 is 2. This is -3 plus, well, 1/3, let me get rid of my 1/3. I'm about to multiply it. 1/3 of a -3 is -1. So this ends up as -4, and that's -4, and that's the same thing we got using the graphing method. Okay. So I'm going to give you the option. There's going to be some problems where I give you a graph. You can use the graphing method or you can use the formula. Every time. I don't care. There's some problems that I'll give you where there is no graph. Or you can do both if you just want to double check. I think in the practice problems I assigned, I give you the option. I went ahead and put a graph underneath the problem just like you saw here. Okay? So the key to this lesson, let me summarize it here real quick for you. When I'm partitioning a segment, we're partitioning it into parts. These are not equal parts. If they're equal parts, then that's something called the midpoint. The midpoint, it's half of the way down the line and it splits it into a 1-to-1 ratio. Okay. Typically, a point that partitions into unequal ratios is when we use this partitioning formula. Like it's going to be 1/3 of the way or 1/4. We're going to split it into fourths. We're going to split it into fifths. Okay. The most important thing is you understand the difference between whether you're given a ratio or if you're given the fractional distance. Here's a hint. You got to find the fractional distance. So make sure you have that formula down to take a given ratio and change it to the fractional distance. Let me explain where the ratio comes up here again. Here I showed you that this part is worth 2 and that part's worth 1. Well, that means this piece right here, that's worth 1 part. This part here is worth 2 parts. There's your 1-to-2 ratio. All right, this is 2 times longer than that. All right, that's how the ratio shows up. How does this point related to the distance? It's 1/3 of the distance from A to B. Pay attention to the keywords like from and to, and you guys will do just fine with that. All right, try to memorize this formula. The partitioning formula, you might see some different formulas online. They're essentially the same thing. Sometimes you'll see these plugged in for rise and run, sometimes you won't. Okay? Anyway, we'll be working on this for a couple days. If you need help in class, please ask for help.